All right, let's take a look at our lesson for today. It's on local linear approximation. I'm going to go ahead and start out by just saying these words, sometimes just students have no idea what it means. And I want to give you the vocabulary word to put in your head. Local linear approximation just means a tangent line approximation. That's all it means. It is very fancy words. They love that notation, local linear approximation. But really, for us, it just means using the tangent line to approximate a value. That's all it means. They love to have this really nice, fancy formula right here. But if you compare it to our just standard equation of a line, it's pretty much the same. This would be our y1. This is our first derivative. You know, the value of our first derivative at x naught is our m, and our x naught is our x1. It's really just a tangent line. So please don't let those words throw you. You'll see them, you know, from time and again the rest of the school year, local linear approximation. And whenever you see it, don't freeze. Just think, okay, that means tangent line approximation. That's all it is a tangent line approximation. Now, there's a couple of different types of problems that you'll see with this. One type is where they give you the equation, and I think that's probably a little bit easier, so that's why I chose this one to do with you, where you don't have the equation at all. And they still expect you to use a local linear approximation to approximate, you know, a value, in this case the square root of 65. So I'm going to work through an example that I think is a little bit more abstract than one that they give you an equation for. All right, so let's work through it. It says use the appropriate local linear approximation to estimate the value of square root of 65. Verify accuracy with a graph. We've talked about using tangent lines before to approximate values. And just as a reminder, so here I have a curve. There's a tangent line. You know, if I am trying to approximate a value close to the point of tangency, it's a pretty good approximation a lot of times. Which is why this is a whole technique of local linear approximation. Because if I can get pretty close to it, I'm in good shape. Now, the farther away I get from the point of tangency, the worse my approximation is. And so we need to keep that in mind when we're looking at what we're asked to do. First of all, we don't have an equation. We need an equation. And we're using square root, so the most logical equation to use would be square root of x. Okay, so that they didn't tell us to use that. We are coming up with that. That's why I was telling you this type of problem is a little bit more difficult because we're not given an equation. So it looks to me like square root of x would be probably a pretty good thing to do. Now, when we do our tangent line, we want it to come out nicely. Otherwise, why use this technique? You know, we want it to be come out nicely. I don't want to try to figure out what the square root of 7 is. You know, I mean, that just doesn't make any sense. So when we choose our x naught, we need to choose one that's close to 65, but that's very doable, that we can really work with, and it's not going to be difficult. 64, so that's what we should do. We should choose our x naught to be 64. Now, did they tell us to do that? No. We're doing that because we think that that is going to be the easiest one to work with, and we want to be close to 65. Because if we're not close to the point of tangency, then our estimate is just really off. So we want to be as close as possible. This one serves, we think, the best choice. All right, so we have our function and we have our x naught. So now we need to go about the task of writing our tangent line. So what do we need to write a tangent line? Or, you know, if you want to use this fancy notation and confuse people, you can use that. What do we need to write a tangent line? We need slope and a point, right? We have the x-coordinate of our point. We just need the y-coordinate. In order to find the y-coordinate, we would just substitute into our equation, right? We get our y-coordinate, so square root of 64. So it would be 8. Y minus 8 equals, and then we're going to skip that for a second, x minus x1. So to get this piece, our slope, what do? Take the derivative, substitute in the x value that we want the slope for. And what's the x value we want the slope for? 64. So that's what we do. So we find the derivative. y prime would be 1/2 x to the negative 1/2, or rewritten. Okay, so I want to use my, again, we're setting up our linear approximation tool with what we know, the 64, and we're setting this up to use it as an estimation tool. So I would substitute a 64 in here, and I would get 1/2 square root of 64, which that would be 8, so this is 1/16. So this is my estimator tool. Okay, this is my local linear approximation tool that we just created. It's basically just our tangent line, that's all it is. And so to use this tool, we want to use it. So keep in mind, I want to discover, say that's of course this isn't the proper graph, I'm just illustrating. Say that's 64. I want to estimate 65. I'm just going to basically substitute a 65 into my estimator, my local linear equation, and that's going to give me my estimate. Okay, with me? That's all you do. You write the tangent line to a point, a closest point as possible. Then you use it to estimate what we don't know. We don't know what the square root of 65 is. We don't have that memorized. So we would write it, go ahead and substitute in the 65. And so our approximation, we do all of our arithmetic, and our approximation is 8 and 1/16, which in decimals is 8.0625. And just out of curiosity, because, I just wanted to know, what would this, what does the calculator say the square root of 65 is? And the calculator says it is 8.06225. So our technique was pretty good. It was pretty close. It was close to, out to the thousandth. That's pretty nice. That's a good estimating technique. And in the higher maths, estimating techniques will become more and more important to us, to have to estimate. So, what our calculators that do integrals for us and derivatives, they are not doing it like we do it. They do it with approximation programs. Okay, the calculators don't go through and integrate by hand like we do. They do use an approximation program. Approximations are powerful and used in a lot of different applications. And this is just one technique to approximate. Just a little baby technique to approximate. We're just learning about approximations, which are important in math. Okay? So are we okay with that? All right, let's go to our second slide. Differentials. So differentials. I do love differentials. Probably in the minority. Some students really are troubled by this, so just kind of stick with me. It's going to be all right. Differentials, we have the definition up here. Basically, dy and dx are called differentials. That's what they're called. That's their that's their name. The definition. So if we have a function, it's a differential function, which means you can take the derivative of it. Then the differential of x is dx. Period. That's like the definition. The differential of x is dx. They're also noting it as an independent variable. And the differential of y is dy. Now, they're a little bit fancier with dy, and they give us, a definition for dy. It's f prime of x dx, and should look familiar to you, but we'll look at that in more detail in just a moment. But that's the basics of what this is going to be about. Now, let's talk about delta x and dx. For our purposes in BC calculus, we're going to set them to be equivalent. They're going to be equal. Do they have to be equal? No. But for our purposes, when we're talking about differentials and we're doing anything with differentials, we're going to make them equal. All right, that's what we're going to do. In the other maths, they may not want them to be equal, but that's not our concern. We're going to make them equal. So delta x is going to equal dx for us. The other thing that I want to point out, now this is a lot of fun. It's just the theory behind the formula that's right here. I've found, over time that students really just prefer to see the formula and not really to go through all of the theory. Maybe we can go through the theory some other time, but all of this theory yields this formula right here. This is the important piece of information that you need to know in this box. That delta y is equal to f of x plus delta x minus f of x. Okay, that's what you need to know. All right, in this box. So this is just the theory behind y. And again, you'll notice that we're setting dx equal to delta x. That's just what we're doing in this application. One other thing that I want to do before I start the example, and is I want to explain this graph because you will be required to graph. dy and delta y are not the same. They represent two different distances. All right, so let's kind of take a look here. First of all, your delta x, you're going to be told, maybe it's 2 or maybe it's -1. I mean, you'll be told what delta x is. You don't have to guess. So it'll be some value. And let's talk about how it's measured. Of course, delta x is going to be equal to dx. The original point that we're going from is the point of tangency. That's where we're measuring everything from, the point of tangency. Notice that I have basically I have two curves. I have a curve and a tangent line going on here. Curve and a tangent line. My dy is the measurement from my original y value of my point of tangency to my new, or basically the tangent line y value. That's dy. dy is the measurement, I'll say it again, dy is the measurement from my original y value at point of tangency to, I go over here by delta x, however much I've moved, and up there, and my new y value that's on my tangent line. Delta y is the difference. So I'm again starting at my original point of tangency. Delta y measures to the function itself. It measures from my original y value to my new y value that on the function. So that's the difference. So dy goes with the tangent line and delta y goes with the curve. Really big distinction. You should write that down. dy goes with the tangent line, delta y goes with the curve, because that's where students get confused. They don't know the difference between them and don't know which one is which. All right, so I'm explaining to you which one is which. Now, let's go ahead and work through the example, and then as we go along, hopefully, it maybe make more sense. What they're wanting us to do is find dy and delta y. They're telling us that x is 4, and they're telling us that dx and delta x are the same, and they're 3. So you're given that piece of information. Doesn't really matter which one we find first. Looks like I found delta y first, maybe just because the equation was right here for me. So I'm going to copy down the equation. Of course, one to add to your memory list. So that's delta y. That's the definition for delta y. It's f of x plus delta x minus f of x. All right, so we know what our function is right here. This tells me to take the function and put x plus delta x in place of x. So my delta y is going to be square root of x plus delta x minus, and then just regular f of x. Okay, so I substitute it into the formula. My next job is to see if I have values for x and values for delta x. Do I? I do, right? They gave them to me. I have a value for x, it's 4, and I have a value for delta x, it's 3. So now I'm going to substitute those in. So that would be 4 plus 3 minus square root of 4, or basically square root of 7 minus 2. Now the decimal approximation for that, just because we're going to be graphing it, it would be good to know the size. It's basically about 0.65. All right, so that's our delta y. We have just calculated this. Okay, dy is a little bit easier to find. We're more accustomed to finding dy. So dy is a result of finding the derivative. dy dx equals 1/2 x to the negative 1/2. And now I want to solve for dy. I would multiply both sides by dx. So I have dy equals 1 over, I'm just going to rewrite that, to dx. Okay, so now I have an equation for dy. I have an equation for dy. And I asked myself the same thing. That once I got my equation, I got my formula, subbed in my formula. Do I have values? Here we go. I've got my formula. Do I have a value for x? Yes. Do I have a value for dx? Yes. So I have to use them both. So 1 over 2, my value for x is 4, and my value for dx is 3. And so that gives me 0.75. So that's my dy value. Got both of them. The last thing that I'm going to be required to do is graph them. So let's do that. And I guess I'll put it down here. What we're interested in an x of 4. So we're interested there, and we are interested in a dx or delta x of 3. Notice it's positive. It makes a difference what the sign is. It's positive. That means I'm going right 3. If this were a negative 3, I would go left 3. Okay? The sign makes a difference. So 1, 2, 3. So I'm interested in the distance, or this space between 4 and 7. That's where I'm interested in. So I'm going to go ahead and draw our function. Okay, that's our square root function. I'm going to draw our tangent line at 4. Guess I'll put it in a different color, hopefully to make it a little bit more recognizable. Okay. All right, so we are supposed to graph delta y and dy. So let's remember what the deal is. So our original y value is here, and we go over to 7 because that's our dx. And so this distance right here between our original y value and our function value is what? Which one is that one called? Between the curve. Delta y. The one in the curve is delta y. This is delta y, which we said is approximately 0.65. Right? The distance between the original y value and the curve is delta y. All right. Now let's look at the distance between the original y value and the tangent line. What is that one called? That one is called dy, which we said was 0.75. Now, is dy always going to be bigger than delta y? No. It just depends on the circumstances. Okay, it's not the case. Because in this diagram that we see over here, dy is smaller than delta y. It just depends on the circumstances. And so there's our graph. We have drawn our graph, and we've labeled those two distances, the one that's dy and the one that's delta y. Okay? Is that okay?